In this video, we're going to be talking about Markov models for discrete valued data. And in general, these sorts of models are called n-gram models. The first one we're going to look at is going to be the first order Markov model. And that's called a bigram model in this case, where the data take discrete values. The reason why it's called a bigram model is, rather than say a unigram model, is that the term unigram model in natural language processing is reserved for the model which puts independent distributions over each item in the sequence, i.e. that the probability of y1 is generated from this distribution, y2 is generated from this distribution, all the way through up to big T. So each item in the sequence is generated independently, i.e. there are no dependencies in the sequence. So in a way, this isn't really a sequence model. So this is called unigram, the first model with non-trivial dependencies between items in the sequence is therefore called a bigram model. So in the bigram model, we're going to imagine that each token in our sequence takes one of k discrete states. So yt can take a value 1 to up to big K, where big K is the number of possible states it can take. In order to specify our bigram model, then we need to specify two quantities. We need to specify the distribution over our first state, and then the conditional distribution of any state given the preceding one, because we are going to tie the parameters of each one of these distributions. And so we just need to write down what's the probability of yt given yt minus 1, and we specified all of these distributions. And the way we're going to refer to those quantities is the distribution over the first state we're going to call the initial state probabilities for obvious reasons. It's the distribution over the first state in the chain. And I'm going to denote that with the symbol pi, with 0 indicating as a subscript that it's the initial state. And this is just a categorical distribution where the pi's will, of course, sum to 1. So if we sum this thing like this over all k possible settings for that first variable, this thing will have to normalize and therefore will sum to 1. So just a standard categorical distribution. The probability of yt given yt minus 1, we can write out as a little matrix in this case. So we're going to define a matrix T, which is of size big K times big K, which indicates what's the probability of landing in state K, given that we're in state L to start with. And again, this thing must normalize over yt. And so if we sum over this matrix down its columns, each column must sum to 1. Okay, so, and this is in general called the transition probabilities of the system, and in general it's called a stochastic matrix because the columns sum to 1. In general here, some people define these quantities using a transpose. So in that case, the probability that yt takes a value k given yt minus 1 takes the value L is sometimes written like this. It depends on where this is L and this is K. It depends on your textbook of reference or particularly what course you're studying. But we're going to define things the other way around, and that makes things a bit more convenient for reasons that I'll discuss on in the next video. This sort of model, of course, can be generalized to a second order Markov model. And here we use the term trigram model, obviously extending the order of the bigram model by 1. In this case, you'll need to specify the following sets of parameters. We'll need, or distributions, we'll need the distribution over the first state. We'll need the distribution of the second given the first state. And we'll then need the distribution of yt given yt minus 1 and yt minus 2, because all of these distributions here will then share parameters. So this new object here, where we have to specify a distribution over yt given the value of yt minus 1 and yt minus 2, this thing defines a multi-dimensional array, which is of size k by k by k, because yt can take one of k possible values. So we need a distribution over yt with k elements. And that distribution depends on the k possible values that yt minus 1 can take and the k possible values that yt minus 2 can take. So we end up with a multi-dimensional array of k times k times k. And if you were imagining using this to model, say, something like written English, in written English, we want to write distributions over characters, and there are the 26 characters that make up English. There's the capitalized versions of those characters, and there's punctuation. So maybe we've got, say, 100 different symbols that we need to define a distribution of at each step in the sequence. If we're going to use a bigram model, we need 100 by 100 parameters in our transition probabilities to describe that. So maybe that's doable. You know, that's 10,000 parameters essentially. So that sounds like something that we could manipulate and learn from data. In the case of our trigram model, this is 100 by 100 by 100 multi-dimensional array that we need to learn and manipulate in order to do forecasting, say, of what the next item in the sequence is. And this thing starts to become, a lot more cumbersome to handle. We need 1 million parameters here. Learning 1 million parameters is going to require a lot of text, otherwise we're going to overfit. So you can see quickly that as the order of the Markov model goes up here, we quite quickly get quite unwieldy objects that we need to estimate from data, these very large multi-dimensional arrays, and that can limit their applicability. And typically you would only use relatively low order Markov models for that reason. In the next video, we're going to just ask some questions about this model and do some basic calculations through those questions in order to get used to handling it.